So this is a good example to showcase the idea that if you have a function that is invertible, that is a function of x, but can be written as a function of y, that you have choice. And we want to find the arc length of this function. Find arc length on the interval 1 to 7. As written, that means the x interval. So x goes between 1 and 7. So let's go ahead and start the arc length formula. The arc length formula is the integral of ds. And ds, I get to choose here. I could do this with respect to x or with respect to y. I'll set it up with respect to x first. And then in a different ink, I'll work it with respect to y. All right. So with respect to x, we get the length is equal to, and with respect to x seems the most attractive because they gave us the interval going from x equals 1 to 7. So x equals 1 to x equals 7. And it'll be the square root of 1 plus the quantity dy dx squared dx. So off to the right-hand side, I'll find out what dy dx is. Remember, y is equal to the natural log, so dy dx is 1 over x. And then dy dx squared, well, that's just 1 over x squared. And I'll substitute that. Actually, no, I'll do 1 plus that as well, because I want to showcase what you should be doing here. So this is 1 plus 1 over x squared. Now remember, that's going to be within an integral or a radical. And so I would like to group these two terms together. So I'll do that. I'll get a common denominator. And now that's what I'm going to put into my radical. And that's kind of nice because that denominator, when I take its square root, is just going to be x, because x is going from 1 to 7. It's positive. So when you take the square root of x squared, it's just regular old x. So that's what I'm going to sub in here. The integral from 1 to 7, not writing x equals. Oh, you also can't see it, but I'm not writing x equals because there's no need to now. We're already completely into the world of x. This will be the square root of 1 plus dy dx squared, which is x squared plus 1 over x squared dx. The square root of that denominator, just x squared plus 1 dx. This is a fascinating problem because you could do this several different ways that I'm thinking of. I'm not going to say that you can exactly do it several different ways, but I'm going to say that right now I see possibly a U sub, possibly a radical substitution, possibly even a trig sub. So those are 3 different ways that I would tackle this. I probably do this problem specifically doing a radical substitution just because I want to. So if you did a U sub just for x squared plus 1, it wouldn't be, you'd end up getting something messy. So I think it would be nicer to maybe try this with a let u equal square root of x squared plus 1. That is, u squared is equal to x squared plus 1. That is 2u du is equal to 2x dx. That is, dx is equal to u du over x. That's kind of the idea that I'm going to go with. Now, obviously, doing that substitution means that our limits of our integrals, those are going to change. So when x is 1, u is equal to square root of 2. When x is 7, 49 plus 1 is 50, u is equal to square root of 50. Or you could write that as 2 root or 5 root 2, but I'm just going to leave it at square root of 50 for now. And then let's see, the square root of x squared plus 1 gets traded out for a u. We still have that x downstairs we'll deal with in a moment. And the dx gets traded out for a u du over an x. And that's kind of nice because I will trade that. I'll write this as 5 root 2. It's kind of nice because in the numerator, we get a u squared du. In the denominator, we get an x squared. But remember, x squared is actually equal to u squared minus 1. And now I'll do long division just to, divide it, because I'm thinking partial fraction decomposition on this problem now. So notice this is a good like final exam style question, because you're using integration techniques while you're doing this. So if I were to do long division, u squared minus 1, some people do this just automatically, but I'm showcasing the idea. U squared goes into u squared once, multiply back through u squared minus 1, subtract that entire statement, and you will get 1. And so this becomes 1 plus 1 over u squared minus 1 du. And now you can go ahead and integrate the rest of that partial fraction decomposition on this. Or if you happen to know that's the inverse, I think that might be the inverse hyperbolic tan, but I don't expect
that
it.
Is.
Yeah. So, but you could also just do a partial fraction decomposition. Now, the other way that you might have thought about tackling this is with respect to y. With respect to y. Because again, when you're dealing with a function and you're asked for the arc length, if that function passes both the horizontal and vertical line tests, then you could solve that function for x and do this all with respect to y. X is equal to e to the y power. And this might, I'm not guaranteeing, but it might be easier, but it's probably not. So let's see. We had the integral originally, x was going from 1 to 7. However, when x is 1, the y, which is the natural log of x, is going to be 0. When x is 7, y is the natural log of 7. Oops, I should write y equals, so that's actually apparent. And by the way, this is the arc length function. And remember, the ds we're going to do is the square root of dx dy squared plus 1 dy. Well, let's see if this gets a little bit easier. It might not actually, but it might. So let's see. Dx dy is e to the y. So dx dy squared is e to the 2y. And so therefore, we are actually looking at the integral from 0 to the natural log of 7 with the square root of e to the 2y plus 1 dy. That is not the best. You could, you could do a u sub here. I'm curious. So I'm going to let u equal e to the y. You might be wondering why I'm not letting it be e to the 2y plus 1. There's a very specific reason. I want that to be a u squared plus 1 in that radical. Then du would equal e to the y dy. Since I don't have an e to the y dy to steal away, I'm going to write that as dy is equal to du over e to the y. Now, doing the substitution, when y is 0, u is 1. Oh, look at this. And when y is natural log of 7, u is 7. And we have square root of u squared plus 1. dy gets stolen out for a du over e to the y, which is u. And we are back at, hold on, wait for it.
Where we were before.
Yeah. But this is kind of nice. It's kind of a cool idea that you could do this both ways, as long as it can be written both as a function of x and a function of y. You have choice. And sometimes you can get very lucky by making the right choice and trying it the other way. It can work out nicely. That's why I wanted to try this, because I thought, well, what if it does work out nice? That'd be awesome. But unfortunately, it doesn't. All right. But that's a good tactic to use.